The graph above shows the speed of a car traveling in a straight line as a function of time. The car accelerates uniformly and reaches a speed VB of 4.2 meters per second in 8 seconds. Calculate the distance traveled by the car from the time 0.3 seconds to 3.8 seconds. So when we look at this, we have a graph, and on that graph we're looking for information for a very specific part of the graph, but we have a lot more information than just what they're referring to. We are looking for the displacement for the periods between 0.3 seconds, so right about there we'll say 0.3 seconds, to 3.8 seconds, right about there. So we're looking for how much ground is covered through that range of time. We didn't start this at 0, and we're not going until 8 seconds, right? So we're looking at just part of this graph to get the answer. But the thing is we do have the whole graph if we need it. Now, we're not covering it in this class, but one thing we can do is we can look at this and say, okay, the area underneath a curve is the distance covered, right? If we have speed versus time, the area underneath the speed versus time curve is the distance covered. So we could find the area underneath this, but we're not going to. We're going to use the equations that we have. So we are looking for a displacement. So we need a displacement equation. Let me erase that stuff. There we go. Okay, good. So there's our displacement equation. I tend to use x. Unfortunately, this one uses d, but we're still looking for this value right here. And we've got to think about what we know. Well, going back to the picture, we don't know the initial velocity. We don't know the velocity at 0.3 seconds, which is the start of this problem. So we don't know that. We don't know the final velocity. We do know the time. This is the time from between 0.3 seconds to 3.8 seconds. So 3.5 seconds is our time. So that we have. And we don't know the acceleration. So there's a lot here that we simply do not know. But time is done. So if I look at this, time, I have that. I'll check that off. There we go. If we had the initial velocity and the acceleration, we could do this problem. Well, we have an entire graph, so now we've got to figure out how we're going to use this graph to get these values. So going back to the graph in the question, we need to find the acceleration, right? We need to find the acceleration so that we could plug it into this equation, right here. Well, acceleration is final velocity minus initial velocity over time. I don't know the final velocity and the initial velocity for the two times specified in the question, but I know the acceleration is constant throughout this trip, and I have two other velocities that I could use. I know at the beginning my initial velocity is 0. I know after 8 seconds my final velocity is 4.2 meters per second. So final 4.2 minus initial 0, and I know the time that it takes, 8 seconds. So I have everything. That's meters per second. There we go. I have everything for this equation right there. I set this up. I am going to have 4.2 minus 0 works out to be 4.2. So I'm going to have 4.2 meters per second divided by 8 seconds. My units work out to be meters per second squared. I'm just going to put it off to the side. My units work out to be meters over seconds squared. 4.2 divided by 8.525. So using the graph, not necessarily this information here, I didn't need this information, but using the graph as a whole, I'm able to get the acceleration. I'm able to get it to be 0.525 meters per second. Again, I just picked points on the graph that I knew the values for. I knew the time between them, and I knew those two velocities. So I can get that. So I have my acceleration. Going back and looking at this, let me erase this. I have two things now. I have the time. Now I have the acceleration. I have the time, it's 3.5 seconds. I have the acceleration, so now It's okay. I have this part done. So now I need the initial velocity. Going back and looking at my graph, I found the acceleration, sorry. There we go. Now I need to get the initial velocity. Well, again, now I have an acceleration. I am looking for the velocity here. Call it initial, call it final. I have choices, but I'm looking for the velocity at this point because this is the initial velocity for the problem. Well, I have an acceleration now because I've solved for it. I can call this my initial and call 4.2 meters per second my final, and I know it takes 7.7 seconds between them. I have another velocity, I have a time. Or I can go from 0 to here. I still have a velocity, and I still have a time. So I have everything I need to solve for the unknown. I'm going to use this initial stuff. I'm going to look for this velocity, because I know my initial velocity is 0, and I know my time is 0.3 seconds. It takes 0.3 seconds to go from start to the time that I care about. So when I look at this, final velocity, which is what I'm looking for, because it's the final velocity for this little piece. Let me change color. Final velocity for this little piece right here. The final velocity it reaches after 0.3 seconds is the initial velocity for the problem. So final velocity equals acceleration times time plus the initial velocity, which is 0. So it's going to be 0.525 meters per second squared, meters over second squared times the time, and the time is 0.3 seconds. So we're basically looking at, if we start from rest, what speed do we get to at 0.3 seconds? What speed do we get to? Well, first of all, let's look at the units. This cancels out this. I'm left with meters per second. And what is my meters per second? It is, come on, 0.1575 meters per second. So I have everything that I need now. Now it's just a matter of plugging it into the equation. Let me erase all this. I have my velocity now because I found it. I have my acceleration, I found it. Both things I can get right from the graph. Right? And again, I'm not really looking at the question, I'm just getting those values. Now I have initial velocity, 0.1575 meters per second, times my time, 3.5 seconds, plus 1/2 acceleration, 0.525 meters per second squared, times time squared, 3.5 seconds, twice. I'm not going to be able to squeeze it in there. Let's see, 3.5 seconds. And I want to write it that way to make a point. Seconds cancel out. This first part's in meters. Plus, I have one on top, cancels out of seconds. Another one on top, cancels out of seconds. I am again left with meters. So I have meters plus meters, and that is going to give me my answer. 0.1575 times 3.5 0.1575 times 3.5 0.55 meters, and the other half, 1/2 times 0.525 times 3.5 times 3.5 works out to be 3.22 meters. Add those together, and my answer is 3.77 meters. And that's the problem. Thank you.